Okay, this is the second part of the Chapter 3 Whitlock Schluter video uh, lecture notes. We're moving on to spread. So the issue is why spread? Three key features of a data set are shape, center, and spread. So let's check this out. What happened to this guy? He was thinking average is 3 feet, but he did not account for the possible variation in the system. Now, let's consider these two basketball teams. We've got Biola Eagles and NAIA School. Eagles have 67-inch tall players, 72, two 76ers, and a 84. 60 inches is 5 foot. So this guy's 5'7", this guy's 7 foot. Over here, we have 72 inches, that's 6 foot even, 73, two 76ers, and a 78, which is 6.5 feet. Okay, the mean of both teams turns out to be 75 inches. Median of both teams turns out to be 76 inches. They're both ordered, and 76 is in the middle. And the mode is 76. There's two with 76 inches. Therefore, the two teams are equally matched, all other things being considered, right? Of course not. We've got the 7 foot tall center who stands 6 inches above the competitor. Better for rebounds, better for shooting and blocking. We also have this 5'7" point guard, which can keep the ball away from the others when dribbling. Okay, so what we need is a measure of spread to tell us to discriminate, because center does not do it. So let's pop back over and see what we've got. We're going to go right after the big tamale, which is standard deviation. Standard deviation is the square root of variance. So population variance, again denoted with Greek symbols, is the sum of I running 1 through capital N, xi minus the population mean mu squared, all divided by the number of elements in the population. Whereas the sample standard deviation is xi 1 through n, xi minus x bar, sample mean, all squared. And we divide by this funny little n minus 1, not n. Comment in a little bit. Okay, that gives us the variances. Now, again, standard deviation is just the square root of population. So I'm taking my square roots here. Everything looks good. Okay, that's going to do it. Now, there's one other measure of spread, which is range. And the range is just the difference between max and min. So what I really need to do is illustrate both the measures of center and the measures of spread. Now, comment on why this n minus 1. We're going to see later that this 1 right here refers to 1 degree of freedom in a t distribution, which is because we've estimated 1 parameter. Now, a heuristic explanation for that is as follows. When we have a population with a bunch of observations inside of there, and we're going to take out a sample, some sample from the population, let's say this turned out to be the sample, then on average we are going to miss the more extreme observations, and because we're squaring, the observations farther away have a greater influence on this number. And so what happens is we tend to underestimate the population variance on average if we didn't use this minus 1. So we subtract 1, we're dividing effectively by a larger number and slightly shrinking that number down, which gives us an unbiased estimator of this value, as can be shown using expected value theory. Okay, now let's consider this little toy data set. Okay, 2, 8, 21, 14, 15. First of all, if there's no mode, so don't worry about that, the median has to be found by putting them first in order. So I'm going to order them here, 2, 5, 8, 14, 21. So mode is none. Median is going to be 8. And then the mean, we're going to take the sum of the x's, and let's get some notation for that just to show how the notation's working. Here's the sample mean. The sum of the x's looks like that over 5, but specifically it's 2 plus 5 plus 8 plus 14 plus 21, which is 50 over 5. That gives me 10. So 10 is my median. Now let's go on to the standard deviation, and we're going to calculate variance in the process. So let's do that variance. Okay. This is a very, very ugly calculation. If you were to actually try to do this, it would look like 2 minus 10 all squared plus 5 minus 10 all squared plus 8 minus 10 squared. And it's so horrible that I'm amazed that I'm actually even doing this for you. It's a waste of our time. But if it helps you to understand something, then we'll do it. Okay. Now, I don't even know what that is, and nor do I want to write any further on that. What I will do is the way that you would at least think of doing this by hand. The difference here, 14 minus 10 is 4, and 21 minus 10 is 11. Okay. And so what's going on here? Well, what's really going on is the following. I'm going to just draw a little graph here from 0 up to 20. And let's stick a 10 in the middle. And let's go 5, 15. Okay, great. Now that I've got that, I'm going to switch colors. And I have the number 2. Stick that here with a 5. We've got an 8. We've got a 14 and a 21. Those are my data points. Now, let's take observations. Distance from 10 there, that's a -2. Okay, this distance from 10, minus 5, and this distance from 10 is -8. Okay, see those values? -8, -5, -2. Those are the distances away from the mean on the left. And on the right, this 14 here is 4 units away. And then that 21 there is 11 units away. And that gives me my 4 and my 11 here. Okay, now, if you add these together, 8, 5, and 2 is -15. 11 and 4 is +15. They add up to 0. That will always happen because of the mean. That's what the mean does. It is a center of gravity. It weighs, it's the balance point. If you were to stick these equally weighted balls on a evenly balanced ruler, let's say, or some type of material that they could balance on, that's the point that they'd balance. So what we do then is we square them. 8 squared, 64, 5 squared, 25, -2 squared is 4, 4 squared is 16, 11 squared is 121. Add this column up, and I get the 230. Okay, now that's squared deviations, or squared distances from the mean. 230 over 4, okay, so that 230 divided by 4 is going to turn out to be 57.5. That's my variance. It's in squared units, which which is not really all that helpful. So the standard deviation is the square root of 57.5, which is 7.58. Now if I come up and look at the 7.58, that's a number that feels like an average of those distances, about 7.5 away from the mean. So on average, these points, 2, 5, 8, 14, 21, on average, those guys are about 7.5 away from the mean of 10. And so now we've got ourselves a standard deviation. Range is 21 minus 2, which is 19. Okay, that's rational. And that does it. But I want to show you what's known as the shortcut formula for standard deviation. Okay, we're going to use this quantity here quite a bit in the future. So the sum of squares x, I running from 1 to little n of xi minus x bar all squared can be algebraically calculated as the following. X equals 1 through n of xi all squared minus the sum of I running from 1 to n of xi quantity squared divided by n. I'm not going to do the algebra. It's a good exercise. If you calculate this by hand, it's so much easier. Let me show you. Let's just do an xi squared column. Well, xi turns out to squared is 4, 25, 8 squared is 64, 14 squared is 196, and then 21 squared is, I believe, 441. When I take the sum of those, I get 730. Okay, so I can plug that into my formula down here, and let's see here, I don't need to worry about that. So SSX is going to be 730 minus the sum of x was 50, so take 50, square it, and then divide by 5, and that is going to be 230, which was my original sum of squares x that I can use up here. Okay,